the output of the timer goes true. So you can see here I'm using the syntax, the name of the function block, open parentheses, the different inputs separated by commas, and then a closed parentheses. This is the kind of all-in-one function block call. It explicitly calls out the inputs and calls the function block in one line. Great for something like this timer block that has 2 inputs and is relatively simple. But if you're using a more advanced function block that has, up to tens of inputs or more, it can be kind of cumbersome, in my opinion anyway, and you may want to assign the inputs kind of throughout the code instead of all in this one chunk.
Okay, so what's going on here is another critical piece, another tool in our toolbox. This is showing you how to delay for some amount of time given some condition. All right, and I'll show you how that looks in the code. Okay, so there exists a function block. If we were using function block diagram, FBD, which is another programming language, we could have a literal block. That block is very often called ton or ton. Okay, it will usually have an input called in, and then the output will be the trigger that says that it's done. Okay, so notice that we have similar inputs and outputs here. Our input to our ton block, which just all this block does, the ton block is all it does is delay. Okay, when we get a signal in here, okay, this goes from low to high. Okay, on that trigger, we'll count for some amount of time, right? It can keep track of how many cycles have passed from within the device. We say 5 seconds, 10 seconds, whatever. After the end of that 10 seconds, this will also flag high, and the code can keep going. Okay, this is also a block, a delay in our code. Okay, so for example, if we want to run a motor for 5 seconds, we might have code that says in one line, turn on the motor. The second line would say delay for 5 seconds, allowing the motor to run. And then the third line would be to turn off the motor. So it appears to work for 5 seconds. Okay, so really important, versatile, useful block this is. So over here, this is the one-liner he's talking about. So theoretically, if you wanted a one-line piece of code, it's wraps. So he's really zoomed in here. Again, I'm sorry, this is kind of hard to look at. This could all be on one line, okay? And this is a one-line delay. What this is saying is that we're wiring a variable start timer to the input of this block. That's the input of this block over here. And we're delaying for delay time. Delay time is another variable we have specified elsewhere that will be the number of seconds. Delay time could be 1, 5, 10, whatever. And then it would just, when start timer goes to 1, or when we call it, when we hit the line in our code, it will delay for the time that you set here in delay time. Okay, just another way to write it, but equally functional, is this one-liner can be written in 3 separate lines, okay, where we wire in, see this is our ton block, we're wiring in the input for our start timer, our Boolean start stop, we're wiring in our option, okay, this isn't what, in our function block we would have a little space here, a little tag that we could wire in the time, right, so like 5,000 milliseconds would be it delays for 5 seconds. Same thing here, we wire in how long we should delay for, and here we're saying go, start the block. Okay, and then it would delay, and then after that it would proceed on to the other code lower down.
It's a little bit coding preference and a little bit usability and readability. So the other way that you can do it is actually to explicitly call out the inputs using this period notation. So you would put the name of the function block, period, the input, and then you assign the value. So pretty much just like...
Yeah, so this is the other, literally the syntax is different. So here we're using this kind of syntax where he goes ton_0, and then he has the inputs of the function, right? When we have inputs to a function, if we have a function like this, the inputs would be like this, where this would be input 1, comma, and this would be input 2, comma. Okay, there's another way to code. It depends on the language, but you could also do, for example, how they're doing it here, ton1, and then it has a property of in. .in that we could set to whatever we wanted it to set to. So in here it would be in1. Okay, and then in the next line, it would be another property of object ton that would be pt, and then we would set that to in2. Okay, so this is kind of where it pays off to know other languages in the past. But if you don't, I'm showing you that these are essentially equivalent. Right, if we have, or actually more like this. Okay, where you could write either of these things. You know, if ton was a generic function here with generic inputs in 1 and 2, both of these would apply in this code. They were equivalent to the compiler, right? The way that the computer understands it is the same. Yes? I don't actually know. I don't know what it stands for. I'm sure it stands for something, but I don't know it off the top of my head.
What's its purpose?
That is the how long you're delaying for. It's a variable of a set number. So if, again, we wanted our motor to run for 5 seconds, we would wire in the number 5 into that. Any other questions?
Is IN the number that the timer starts at, or?
No, this is actually a flag. It's a Boolean, 0 or 1. And when it goes to 1, it triggers, pretty much. It's like the left hand of our block here.
A super common mistake that happens when you do it this way, the way we're doing it on the bottom, is you forget to call the function block. So you assign all the inputs, but you never actually call the function block. So you have to remember to put this function block call inside of your code, otherwise the function block will never execute. So the syntax for that is just the name of the function block, open parentheses, close parentheses, and of course our semicolon to terminate it. So don't forget that part, or you will be very confused about why things are not working. All right, let's hop over to our software here. So this is, again, B&R's Automation Studio. It's the IDE for any B&R industrial automation.
So you guys probably haven't seen this before, but this is a great example of showing you what other IDEs look like. Again, you know, the things that we learn in this class in concept and the languages that we're learning can totally apply. It's all standardized. But the UI, like the graphical interface that you apply, will vary depending on the brand that you use, the brand of PLC. So this is, he just said it, whatever brand with their IDE and their special ways of doing things. But you'll notice that the ladder logic is still the same. We're still placing the same symbols. It still looks very similar. Structured text, the syntax is all the same. Just what like windows are where and where the compile button is and all that stuff is slightly different. Okay.
Other IDEs we're pretty much just the same in the context of structured text, but this is what we're looking at today. Okay, so on the left side of our screen here, we've got our structured text. So this is just a standard all-in-one structured text program. So right now we're writing inside of our cyclic task here. So this part here. And then on the right-hand side, we have what we went through last week. So last week when we looked at our ladder logic, we kind of went through and looked at some samples of the different types of logic that you can do. And so that's what we're showing here on the right-hand side. So what I thought would be nice is if we look at kind of a one-to-one comparison to see, hey, what does this line look like inside of structured text, so that you can start to get an idea of how to program your structured text. All right, so let's start with the first one. When we're looking at the ladder logic, this is just a normally open contact tied directly to a coil. If we wanted to do that, this is just an assignment in structured text. So instead of having contact in a coil, we're basically just going to directly assign normally open to output using our notation of colon equal sign. And that's really all we need right there. Moving on to the next one. Used to programming ladders. Well, how I do a normally closed contact. It's really simple. Actually, all you need to do is have this not here. So you can think of the not as a normally closed. So essentially, if normally closed is true, then output 2 will be false, and vice versa. Okay, so that not is going to kind of invert whatever normally closed is. Okay, so that's how we can use a Boolean operator to kind of simplify what we're going to do inside of ladder. Now, looking at number 3, this was our AND statement on the right-hand side here, right? So we're looking at input 1, input 2, and output 3. So because they're in series, that's going to be an AND statement. If we want to do that in structured text, I think it reads a little bit easier. So all you have to do is output 3 and then an assignment of this Boolean operation here. So this AND works the exact same way as what we have here on the right-hand side. So we would say input 1 and input 2, then that's going to assign to output 3. So if input 1 and input 2 are both true, then output 3 will be true. If either one of them or both of them are false, then output 3 will be false. Okay, so let's, it may make sense to actually hop in here and show a quick example of that using our watch window here. So let's just drag output 3, we'll drag input 1.
So what he's doing here, we actually have access to this too, is we have a watch window. If you guys go up into your toolbar, into the Windows list, root around in there, there is actually a watch list or a watch window. And that's when you can, just like we were doing with live debug, where we can keep an eye on the current status of things in our sketch, you can drag variables into your watch window and just have them all in one place, all in one shot. What are the variables, the outputs, the inputs at a given time? Or the ones that are important anyway, you could have a short list of those. So that's all he's doing, is what he's doing is dragging it onto that watch list, and then he can keep an eye on it in live debug mode. Another thing that's worth mentioning is that he has parentheses in these. For example, he says output 3, and he's setting that equal to output 1 and 2. I believe the syntax will still work even if you don't have the parentheses there. But what you can do with parentheses is instead of doing multiple chains, you could do chains of chains. For example, you could do like A or B, and then parentheses, and then you could OR that with another, chain of logic, C, maybe, and D, for example. Okay, and then you have these individual ones. These will figure out, should this be a 0 or 1? Should this be a 0 or 1? And then those two will be ORed together for the final solution.
And we'll drag input 2, so I can see we've got them all here. Okay, so just to kind of prove this out, let's say input 1 is true, input 2 is false. You can see output 3 is false. And if we set input 2 to true.
I'm going to slow this down just a little bit for this part.
Now, see up here, add input 1, and we'll drag input 2. So now you can see we've got them all here. Okay, so just to kind of prove this out, let's say input 1 is true, input 2 is false. You can see output 3 is false. And if we set input 2 to true, now output 3 is true. So it's really that simple in structured text. You just use this and you're pretty much done. Okay, so let's move on. We'll take it out of watch. If there's another one, we may hop back in there. Okay, so number 4, rung number 4 that we looked at was an OR statement. So again, this is what it looks like inside of ladder. If we wanted to replicate that rung, just as that simple rung, again, we can use a Boolean operation. We'll just use OR. So again, it makes it a little bit more readable. So input 1 or input 2, assign that to output 4. So if either input 1 or input 2 are true, or if both of them are true, then output 4 would be true. All right, so the next one we looked at was kind of a tricky edge case, and that's the exclusive OR statement. So what if I want something to be true when either input 1 or input 2 is true, but not when they're both true? That's what we call an XOR or exclusive OR statement. In structured text, we can cheat a little bit. We don't have to do this kind of funky, normally open, normally closed stuff. We can actually just type XOR. So that one's a little bit easier. So input 1 XOR input 2. And we can take a quick look at that just to prove that it works, since it's a little bit of a trickier one. So as our watch window opens up here, I'll just drag output 5. So now we can see that because input 1 and input 2 are already true, you can see that here, output 5 is false. Okay, that's because it's an exclusive OR, which means that one or the other, but not both, need to be true in order for output 5 to be true. So if I, for example, turn input 2 false, then you can see output 5 is true there. And similarly, if we were to do it the other way around, input 1 false, input 2 true, that's going to satisfy our condition for XOR. Now output 5 is going to be true. Okay, so moving on, let's look at function block call. So we'll look at the two different ways here. As a reminder, this is what it looks like inside of ladder. You've just got kind of a graphical representation of your function block, and then you're tying the inputs and outputs to it directly. Here we've got, this is the inline function block call. Okay, so ton_0 is the name of the function block.
So just to drive this home, because some of you might not have worked with a T-on block before, Metaphorically, if you will, this T-on block is kind of like a delay fuse, where if we put in a 1 here, right, we light the fuse, some number of seconds later, it will continue to propagate down the line. So something that we'll do later is you could have this T-on block in ladder logic or a function block diagram where you had your button on the left, right, your contact, you would wire it into your T-on block. And for example, if you wanted something to happen 5 seconds after you touched a button, this is how you would do that. Okay, if you wanted to turn on motor 1 5 seconds after you press the button, like so. Okay. And so all he's showing you here is what I showed you earlier, which is that's what that block actually looks like from the function block diagram or from the ladder logic diagram. But this one-liner right here is all you need to delay whatever you're doing by some amount of time.
And then we've got 2 inputs. One is in and one is PT. So in tells us when to start the timer, so we're going to assign that to output 5. And PT is the elapsed time before we want the output of the timer block to go true. So in this case, we're going to say 3 seconds. So this is the structured text literal for time. So T, capital T, hash 3S would be 3 seconds. Okay, now what we're not showing here is actually the output, assigning the output. So if you wanted to assign the output, you would just type the name of the function block, put a dot, and you can see it gives me all of the options there. So Q, and in this case, if we want to make it the exact same, we would assign that to timer out. So that's how we would make our assignment there. Okay? All right, now let's look at the alternate way to do this. So this is kind of the selectively calling things out. I'll uncomment it real quick so it's easier to see. So in this case, we're actually calling out the inputs individually instead of all in one line. So you can see here, it's the exact same thing. I've got output 5, and then I've got my T hash 3 seconds for my elapsed time, and then I call my function block. Again, don't forget to call this, otherwise you'll be kind of banging your head against the keyboard trying to figure out why your code is not running. So that is the alternate function block call. And then the last thing I wanted to show you in here is a sample for loop. So again, let's say I wanted to manipulate my array somehow. So let's actually hop in here and look at this. So you can see here in my code that I've got an array called my array. And what I want to do is alternate the value of my array. So my array is an array of Booleans. So they can either be true or false. And I want, based on whatever the first value is, I want them to alternate through the array. So if you watch my coding best practices episode, you'll know that anytime you're looping through an array, you should use this size of function, which is a memory function that can give you the number of elements in an array. So instead of hard coding that, you can actually calculate that on the fly. It makes your code much more scalable.
I wouldn't worry about this too much, although it is good practice for beginners like you guys. We typically always know what size our array is. But for example, this allows you to not really care, or it's for the computer to figure out how big that array is. It's just like, here's where the array is, and then this line of code does the calculations it needs to figure out the length of it, right? How many elements are in that array at that current time. But if we know that our array is only so big and it'll only ever be that big, then hard coding it for our purposes is just fine.
So just a little plug there. Go check that one out if you haven't already. So what we'll do is we'll loop from I equals 1, because again, we want to, our array starts at 0, but we want to start from the second element. So we'll start it at 1 and go through inval, which is this value that is calculated here.
Sorry, that's another really good call out. Worth mentioning that if we want to get the first element of our array, right, like the first thing in there at all, the thing that's filling up the array, if we only have one thing inside of there, we would actually call the 0th element. So for example, if we had an array A, to get the first thing inside of that array, we would have to reference the 0th position. Okay, this is what's called 0 indexing. Okay, a lot of things will be 0 indexed. Yeah.
So do arrays start from 0 instead of 1?
In this case, yes. Yeah. So like Python, for example, doesn't start from 0. Python, if you wanted to get the first thing in the array, you would call A1. But this isn't Python, this is structured text, which is a zero-indexed language.
And then basically what we're going to do is we're going to assign to that array element the opposite of the one before it. Okay, so not my array I minus 1. So let's pull that into our watch window, and we can see that that works. Okay, so since my first value is false, my second one is going to be true, and so on and so forth. So again, let's take a quick look at that. Let's say we're on I equals 1. Okay, so the first round through our for loop. So when I equals 1, we're going to be looking at my array 1 and assigning it not my array I minus 1, so 1 minus 1, so not my array 0, which in this case is false. So since it's a not, it's going to flip it to true, so my array 1 equals true. Okay, so you can see how as we go through, that's going to kind of flip-flop back and forth between the different values. So let's just prove that this works. Let's say we...
All right, I believe them that it works. Any other questions based on what we saw so far? Cool, so that's the gist. You can do an incredible number of things with what he just showed here. The building blocks here can really, you can run factories with this stuff, I swear. Combinations of and logic, or logic, delays, timers, just the combination of that really is enough to do 99% of things. After this, we're going to go into some of those practicalities now that we've gotten through that. Again, that video is inside of this PowerPoint. It's also linked in the web resources online on the Harper Blackboard. Additionally, I put in another example in here that kind of touches on all of the basics again. We have a conditional in here. We have an if statement. We have a timer in here, right? A delay. We have comparisons, greater than, less than, setting variables, all that good stuff. So if you guys forget the syntax, forget the vocabulary, this is here as a reference for you. You can always go back to the PowerPoint and check it out. All right, so that's it for structured text. If you have any other questions as we keep going here, the lab this week will be on structured text, but I'll give you a heads up on what it is and how to do it. So if you have any questions, you can let me know. But otherwise, we're just gonna keep going to other content. Any other questions? Okay. All right. Okay, so one thing to get into, I've referred to this process before. It's that PLCs are designed to run their code differently. It's in a much more safe and reliable and understandable fashion than microcontrollers typically run. So your typical microcontroller, your small pocket calculator, your Arduinos, things with processors in them, have code that is created from a compiler. So we write down code in our IDEs, if else, do this thing and do that thing, run calculations. And we more or less assume that it'll run the first line, and it'll run the second line, and it'll run the third thing. Reality is that's not actually how that works. Compilers are kind of black magic in that they started out compiling to machine code those instructions literally, do one thing, do the next thing, and another thing. But they're not actually that straightforward anymore. They are very intricate machines that will try to do the outputs that you programmed them to do in reliable ways that they're programmed to do, but they don't necessarily run like we would expect them to, meaning one line after another. We can have things like race conditions, for example, where we have two processes running at once where they might interfere with each other, trying to use the same resources, read from the same things, write to the same things. If one thing's trying to write something, says it should be high at this moment, another thing says it should be low. It's not always reliable what can come out in situations like that. In any case, PLCs are designed to avoid that problem, so they have very discrete steps in the way that they work. So remember, we have different task groups. We have fast task group, slow task group, idle, and init, which is boot, essentially. And every time each of those runs, so the fast task group is like every 10 milliseconds, I think. So 100 times a second it will run. Slow will be 1 times a second. This is what we mean by running. Okay, so what happens is that the PLC will kind of freeze time. It'll go snap. What are all of my inputs at this current instant in time? It'll read it in almost instantly from I1 through I8, and it'll save that record. And then it'll pass that record. What are all of my inputs at this instant in time to the program? And then it'll run calculations on those inputs. So that's when we'll kind of go line by line, rung by rung for our ladder diagram. Our inputs are here. My program is evaluating all the way down the line. And then we get what should our input or our outputs be, right? We run the calculation, what should things be? And then we actually write them to reality. We trigger our relays, right? Switches get thrown, things like that. That has a discrete stage that happens after our calculation stage. There's actually another more advanced step in between run program and adjust output, which is a communication stage. That's when we have like PLC to PLC communication, logging for talking to the internet. That'll happen right here, things like that. But otherwise, it'll just go right to the outputs, right? Turning things on and off. Writing to our transistors, so to speak. And then we start it all over again. So this is, our program is said to have run. It is now 10 milliseconds later, and we're gonna go and run that program again. We're gonna refresh our inputs. What are they now? In this new instant in time, 10 milliseconds later, in this new reality. And what should we do with those inputs, and so on and so forth. Okay, this is called the scan process. Okay, this is different, again, from other interpreted languages like Raspberry Pis, Python, C, C++. PLCs are kind of their own beast here. They're very much designed to be like this with reliability and ruggedness in mind. So now we're going to get into some more nitty-gritty of process control. So this could be a whole class, and it actually is a whole class that I took in college on system processes and system control. We're going to keep it simple, but I want you to know the parts and pieces of it, okay? Like the vocabulary of what we're dealing with. This will be a little vocabulary heavy, but try to stick with me. Each of these boxes are bins, are small systems, okay? So, for example, if we're trying to keep our car running along the road, okay, if we're trying to have a set speed as the car travels along the road, we're probably traveling at some velocity. We're going to have some disturbance from the outside world, right? Wind pushes back against us. We hit more friction on the ground, which is slowing us down. That affects our system. Okay. We also, from the previous millisecond, probably have some sort of acceleration going on, right? There's explosions happening in the motor. We have some sort of forward momentum. We previously just told it to go forward if we were pressing the pedal, right? We have some of that from the previous second affecting that too. And all that is affecting our system. What our system is it's the car. It's the mass of the car, the current acceleration, the current velocity, the direction it's going. It's the physicality and the responsiveness that can be actually, like, we can mathematically model that in a system. So if we say a certain disturbance happens on that system, if the wind blows harder, if there's less friction on the road, if we have more or less acceleration, the system will respond accordingly. That's called modeling, process modeling, system modeling. Okay, we can actually learn to predict how to affect the system if we properly model it, but more on that in a little bit. So we have a system, we have our car that is existing in the world. It has a measuring element inside of it. In this particular case, it would be our speedometer, right? We have a speed sensor inside of the device that is giving us feedback on the current speed of the car, okay? This is our control point. This is our control system right here, right? So we have a current set point. Say we have engaged our cruise control, right? So it's trying to keep, the car is trying to keep itself at a common speed. We have a set point. The set point is the speed that we set it to, say 50 miles an hour. We have a value, this is the speed that we're currently traveling at, say it's 48.5 miles an hour, right? 1.5 different. And then we have the error. That's the difference that I just told you between the set point and our value. That's the 1.5 metric, right? We are faster or slower by some amount. We're off by a little bit. That gets all fed into our controller. That's the computer living inside your car that gets this error rate. Pretty much all it sees, or all it really cares to see, is the amount of error, the difference on where it is and where it wants to be. Based on that error, based on how big or small that is, it'll give a command to the thing that can actually affect the system. In this case, it would be, the engine. You push the accelerator, you command the motor to give more fuel into the injector, into the engine, and you get more force as a result, right? The feedback is the effect that comes out of our system as a result of the command. Okay, so all of these are actually very formal words in the world of process control and system control. Things like disturbance, feedback, effector, measuring element, set point, controller, error, all critical concepts to understand as we go forward. Also important to understand, more terms, very critical terminology, is talking about systems and how they can not be ideal or how they can be made better. Okay, so for everything that we're trying to do, for our speed controller, for example, if this is our set point, okay, and this is 50 miles an hour, and we're starting at a dead stop, we, even as humans, will have some kind of control system in our heads that wants to get up to this line as fast as possible, overshoot as little as possible, and be as close to that set point over time as possible. Okay, all those as possibles that I just said have vocabulary to them to track how close or how well we are eliminating error over time. Okay, another critical vocabulary is our control variable. Our control variable in this case would be our speed, our acceleration, right? So CV, control variable, our speed in this case. The maximum error is how far away at any given time are we from our control variable. If we're starting from a dead stop, technically the maximum error is actually very, very large. It's like the whole range, 50 miles an hour, as the definition of this error. If we're going on for a very, very long time, or we have a very, very, we're only looking at a window, for example, maybe we're only traveling for a while, after like an hour, okay, and the maximum disturbance that we had over that hour time, the maximum error was only this much, okay. The response time, really important. There's an idea called an impulse. An impulse is like applying a force for as little amount of time as possible. Like if you wanted to strike something, if we wanted to make a really tall peak on a force graph, you would want to hit it as fast and as hard as possible so we get a really strong peak. Okay, so this is an impulse. Okay, if we shock the system as fast as possible, what will happen? Okay, and often what we're actually looking for is the response rate. Okay, if we hit a system, if we shock a system, for example, if I hit a car, if I just have a little Hot Wheels here, okay, and I hit it with some nearly instantaneous force, what will be the speed response of that car? Okay, and it might look something like this, where it will quickly shoot up the speed, and then as the car moves and slows down, the speed will decay, and this will be the response time. Okay, it's kind of hard to see why this might be important for a Hot Wheels car, but this becomes much more important when you're trying to control a process. For example, I was trying to recondition an old incubator. my lab that I was working in, this is a real story, bought an old cell incubator from the 1970s. It was like old and yellow and beige and everything. And the guts didn't work. I had to replace the electronics inside of it. So I needed to put a temperature controller in there because we needed to keep the cells at a certain temperature. And they had a nearby tank of carbon dioxide. A certain amount of concentration of carbon dioxide inside of that system had to be maintained at all times. But it was really tricky to get that carbon dioxide to be the right amount, because if I pulsed the system, if I let in a lot of CO2 for just a second and then turned it off, the sensor that I was using had a really long response time, all right? This would be like my dosage, and then what I would actually see on the sensor would be this. Okay, and this was like 15 minutes later. Okay, that sucks to control. That's really difficult to control, having a really long response rate. Same thing, for example, if you're trying to adjust the temperature of something. Okay, if you give just a little bit to the heater, and then if it changes a lot or a little bit, you know, is really dependent on how easily you can affect that system, how easily it changes. So this would be the response rate. This is also why diabetes is still a problem, actually. So you guys have probably seen that people have been getting insulin pumps. Yeah? Oh, okay, so she knows all about that. There's been a lot of really cool stuff going on for insulin pumps. Essentially, like, can we control glucose if we have someone's glucose that's going all over the place? Can we give insulin at just the right points and just the right amount to counteract that? It's a really difficult problem, actually, because if your glucose is high at this point in time, you don't actually know what it's going to look like down here when the effect actually kicks in as a result of that medication. So it's a difficult control problem if whatever we're affecting here doesn't come into effect until 15 minutes later. That kind of response time can be very difficult to manage. So that's response time. Also settling time. Okay, if we give this impulse, how long does it take to come back down to some percentage of what it was before? It can be called settling time. Okay. Another thing that you guys will very often encounter, at least in DC electronics, is an RC delay circuit. So we can actually make, you guys saw that T-on circuit, that timer block, we can make that with passive electronics. If we have a, if we have a voltage here, plus rail, and this is attached to a capacitor, and that capacitor leaks a little bit, there's a resistor on it. The voltage at this point will change. So if we pulse it, it will, without the capacitor and resistor, it'll look like this. It'll be a perfect square wave, right? Low to high to low. But with the capacitor and that resistor, it will charge quickly. Whoops, sorry, it's supposed to be here. It will charge quickly, and then it'll discharge slowly. It'll have this decay, because it takes some time for the capacitor to completely discharge, and the resistor keeps that capacitor from discharging right away. It's kind of like a slow leak in a bucket. So we pulse high, and then the settling time is actually quite long. And the settling time, T, is related to the size of our resistor and the size of our capacitor, for example. Okay. But when we're talking about the settling time, it's, you know, how long does it take to get to one point to some percent or even zero all the way back down. Overshoot is a really critical, let me redraw that. Overshoot is when we get a little bit too overzealous trying to get where we want to be. So for example, if we're heating something, but we don't want to overheat it, you know, if we're like heating eggs or something, we're trying to incubate eggs and we'll kill the chickens inside if it gets too hot, we want to eliminate overshoot. Okay, so if this is the temperature that we want to keep our chickens at. We want to sidle up to that if we can, right? What we don't want to do is shoot straight up, blow away past our set point, and then come back down sometime later, right? The most effective, I guess you could call it that, sometimes the quickest and least error can come from way overshooting your set point. You'll get a controller that looks like this, it'll like way overshoot, but it'll come down super fast. And you're like, wow, I hit my set point in 0.5 seconds. And it's like, yeah, but you also overshot it by 20 degrees, so what's the point? Something to be aware of is the term of overshoot. This one's important too, residual or steady state error. See here the difference between our ideal value, that's being at like, 0.0000 error, and where we end up beyond that. This often comes up in servo positioning, for example. If we had a tilt controller, okay, if we had a tilt table, we had something like this, we had a tilt table, and we had a little actuator here, all right? Say we knew from some sensor what this angle was right here. We were trying to adjust that to 90 degrees, so we would get perfectly accurate, right? Maybe there was like a rolling ball on here that we're trying to balance or whatever. If we are always not quite level, okay? If after a correction, we were really darn close, but we were just a little bit off, like 0.01 degrees off, and we were always that amount, that would be our steady state error. It's kind of like, no matter how close we got, we were always just this close. If we tried to correct, maybe our smallest step brought us a little bit over the line, and our smallest correction would only bring us a little bit above or a little bit below that line. That would be our steady state output, or our residual steady state error, rather. Talking about dynamics of a system, there's different responses that we can call. All right, so we have our ideal response, our critically dampened response. The best example for this is shocks on a car. If we have a critically dampened car, which means well optimized car, and we drop it from a height, like a dune buggy or something, it'll come down, it'll reduce all that force, and then it'll gently rock back up, right? Like really easy, really gentle. An underdampened high gain system will oscillate. So it'll go down and then it'll shoot back up and then go down and shoot back up until it rests to where it wanted to be. The critically dampened system will go down and it'll come back up, and really low amounts of error, it'll be right back where it should be. An underdampened system will still, all of these in steady state will have a really small amount of error, by the way. It's just about how they get there. Okay, the underdampened system will kind of like ride up. Okay, so it won't pop up from the ground to where it needs to be. It will go foomp, and then it'll kind of like slowly rise back up, for example, in this particular example. Okay. So again, critically dampened is ideally where we want to be, where our response gets us to where we want to be fast and without overshoot or undershoot. Okay, this is also called undershoot, overshoot, undershoot. And this is another example of a control system. So there's two different kinds of control systems. Well, there's many, but this concept of open loop versus closed loop. Essentially, open loop is on the left here. It's kind of like we have a general idea of what will happen when we have a certain output, and we just give that output to the world and hope what we have happens. Motor speed, for example, if we know that we apply 50% of the voltage, if we have a 12 volt system, we apply 6 volts, we know it'll go a certain speed. If we apply the full 12 volts, it'll go twice that speed, for example, or half, depending on how you look at it, right? So that's an open loop control. where we command the motor, but we don't really know how fast we're going. We kind of know how fast, 10%, 100%. And we have an idea that generally in a situation when we apply 80% of our power, we'll go this fast. Okay, that's an open loop system. You're kind of trusting that your output is what you tell it to be. It can't deal well with disturbances though. So for example, in our ideal situation, if we have a controller that's saying, okay, on an open flat road in the desert with no friction, I can run the motor at 2,500 RPM and I know I'll be going at 50 miles an hour. So I should rev that amount and that'll be good. But if it hits a bump in the road, or here when it hits a hill, that naive approach, that open loop, doesn't account for that hill. So when we hit it, the car slows down as a result. We're still driving the motor with the same amount of force. We have a small disturbance here. We have a small amount of error, a difference between our set point and the actual reality. That's our open loop. We don't have a sensor typically in this situation, by the way, or if it is, it's not patched into the control loop. There isn't a computer that's saying, okay, based on our current speed, we're going to do this other thing now in an open loop. Closed loop, we do have that computer, right? There's an accelerometer, or there's a speedometer that's talking to our autopilot computer, or our what do you call it when it's not autopilot? Cruise control. It's talking to our cruise control computer, which, every instant in time it says, I know you told me to go this speed, but we're going a little bit slower, a little bit faster, and it'll command it appropriately. So as we hit that hill, we get that disturbance and additional force we need to apply to the vehicle. Our engine can respond appropriately, which means that our set point, which in this case is the vehicle speed, remains very close, low error, right, to what it should be. Some more vocab for you. Here's our good old overshoot. Overshoot is typically talked about in percent, size of the signal. Okay, so 0 to 100%. If we go 10% over that, it's 10% overshoot. Steady state variability is really important, especially for things like speed controllers, right? For our cruise control, it matters if that can keep you at that speed plus or minus 1 mile an hour versus plus or minus 5 miles an hour, right? That might get you into trouble if when you're on the interstate and it can't quite keep the set point where it needs to be and you end up 9 miles and over and get pulled over, right? So a lot of graphs will be like this, where we have two different colors on the graph. We have the actual measured value, which is in red here, and our command value, which is in blue, right? So this is what we're telling our signal to do, and the red is how it responds over time. So we're turning heaters on and off. You'll see square waves that'll go on and off over time. We're commanding a motor to have more or less velocity. It doesn't necessarily strictly have to be a square wave. It might also be a variable wave, right? When we're moving our accelerator, commanding the motor to use more or less force, right? Rise time and fall time. That's what I was talking about over here with our RC capacitor example. If we have a step response or an impulse, just like this would be the rise time, right? How curved is this? And this would be the fall time. How long does it take to go from this point? Typically, it's something like 80% of the value of the decay value would be the decay time. All right, so we talked about this concept of error reduction. There's lots of different ways, different techniques and algorithms to try to take sense, where we are in the world with our sensors, what we previously commanded ourselves to do, and to try to figure out what to do next. One really common control scheme for that is called PID. It's called proportional, integral, and derivative control, which is actually what I'm showing you up here. I'll get into it a little bit more. But all of these things is just a twist on what I showed you guys before, where we have some input, some disturbance. We have a controller that takes that disturbance and figures out what to do with it, and then applies it to our reality. It's often called a plant or a process. This is like a chemical batch that we're trying to affect, or the temperature of a vat. It's often called a plant. This would be our vehicle in the previous situation, in the previous scenario. But again, all of these algorithms, they're just trying to drive our error, E, to 0, or as close to 0 as possible at any given moment. And they all have different ways of dealing with that. So that's whenever you see an E in this, so E, 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 that's just the error term, is that what it's, how that term's being dealt with, essentially. The first way that it can be dealt with is with so-called bang-bang temperature control, or bang-bang control. This is like baby's first control algorithm. It's if I have a processor and really simple logic, how can I control something to get where I want it to be? And it really boils down to, for example, temperature set point. If temp is less than set point, then heater is on. Or I guess true. Else heater is false. Okay. If we're not where we want to be, try to get there. If we are where we want to be, stop. Bang bang control, on off control. Okay, so here what we're seeing here is, for example, if we want to try to regulate our temperature, this is the actual tank temperature that we're reading here. Okay, how does that tank temperature respond to when we turn our heater on and off? So this is what I was talking about, our process control variable, where we're turning our heater on, which is 1, or turning it off, which is 0. If we were to turn it half on, you would see it go up to the 0.5 mark, but I guess it's not a variable heater, right? It's just on or off. And this is how the temperature responds accordingly. So you can see shortly after, whenever we turn the heater on, we get a little spike in our process, right? We turn it off, it cools a little bit, we turn it back on, it starts to heat up, and so on. And we might have other disturbances in that system as well. So for example, this tank might be outside, and then so they're showing how not only does the temperature increase, you know, we have these little peaks from our heater, but you also have this low frequency rise and fall that is coming from the sun. That's another disturbance in our system that is causing the temperature to change outside of our control. Okay, so this works, right? If you need to get something done quick and dirty, but it has downsides. There's it's naive, it's easy. There's a reason why everything doesn't run on this. It's because it can be done better. Okay, one way that it can be done much better, or I guess one pitfall of bang-bang temperature control really happens when we're trying to use relays as our control element. Okay, as we approach our set point, weird things happen. Okay, remember I told you guys that when we have a temperature sensor, there's some amount of noise on that device, right? The input signal that we get, the analog, I think there's someone behind you. Do you want to let him in? Unless it's just a guy peeking in the room. Okay. All right, so in real life, signals are noisy. Okay, inside of a room, if it's 72 degrees in this room, you would expect a temperature sensor to be like, bam, perfect 72 degrees all the time. But that's not actually true, right? People are coming in and out of the room, it's changing temperature outside, the heaters are turning on and off. The actual reality of the situation is that the temperature is much noisier than that. It's all over the place. It might drift down, it might drift up, it might have peaks, whatever. It's noisy, okay? When we have bang-bang temperature control, every time it goes under and over our set point, our relay is going to click on and off. Okay? This can be fine if this change is pretty slow, right? But if it's fast, if it's a high frequency change, we can wear our relay out. Where if we're really super zoomed in, for example, I'll make a thicker plot over here. If it really like hovers around the set point here, okay, if we zoom in here, and this is what it's actually doing, every time it crosses this threshold, our relay will click, it'll trigger. Okay, so if our relay is clicking like 100 times per second because it's really close to our set point and it's like, oh, we're 0.1 degrees C over, I'm gonna turn on the relay. Oh, we're 0.1 under, I'm gonna turn off the relay. It might last 2 days before you burn out that device. And certainly annoy the crap out of anyone who hears the clicking all day as you're trying to regulate the temperature in the room, okay? With MOSFETs and silent devices, that might not matter as much. You might be able to get away with a bang bang, but it's just implications of why this isn't the end all be all and why we can do better. The way that we can do better is just by changing our bang bang just a little bit. And the way that we do that is with this term called hysteresis. Hysteresis is a very interesting term. It's kind of difficult to understand, and it has multiple definitions. By the way, hysteresis is also a material properties thing. It's how metal, for example, can expand and contract volumetrically as it's heated up and cooled down. But hysteresis is a technique that we can employ to shift the set point just a little bit out of the way of our noise, which means that it won't constantly be triggering all the time. So for example, here in our section, imagine that the first time that we cross the threshold, so right here, sorry, I drew these at the peaks and valleys, it wouldn't actually be there, it would be when we cross the threshold. So here and here and here. When we cross the threshold for the first time, our hysteresis technique would shift up the set point. So after this point, the set point is now here. Or actually, for a temperature controller that we're trying to heat it with, it would be here. Okay, it shifts down. So for all the points after this point, we are now well above our set point. We no longer have the risk of repeatedly triggering it, because see how much space is now here between our set point? Eventually, we'll cool back down, right? So if we're here over time, we'll eventually cool down to our new set point, right? O set point was up here, new set point is down here. We'll eventually cross it again, but when we do, we'll restore it back to where it was. So now we have distance again. So if we have our noise problem on the way down, if this is changing a lot, our set point's now all the way up here. We have clearance. We aren't constantly triggering it all the time. Okay, so this is the concept of hysteresis, okay, and changing set points. So here is another example on where our set point changes, okay? So here we have the original switching state. This is like a temperature controller or a pressure controller, actually, when we need to increase the pressure and when we need to not. This was our original threshold, and when we hit it, it raised up here. Okay, and then would have to lower again underneath this threshold, or sorry, this threshold, before we will turn off our output, right? So this becomes a dead band. Okay, so anywhere in this region, it could go up and down and bounce all around all it wanted. We still know that we're where we want to be, more or less, right? Our control system should chill out. It should wait for it to come down until we pass that again, and then we can turn it back on. Hysteresis. Any questions? Cool. All right. Cool. Making good time today. So this will be our last slide, but it's a doozy. PID. Oh, come on. I have to be like strategic with this. Okay. All right. PID is actually this chart that I showed you before. It's a specific control algorithm that is like the simplest and most effective one that's used, I guess you could say. There's definitely more effective ones out there, but they're not as simple. This is kind of like the first one that really took off to see large amounts of usage because it's so good at what it does and it's easy to set and tune and understand. So if you buy a box off of Amazon, a little temperature controller box, it'll, tell you what degrees it is, and you could, set it up or down. Usually you'll have a little temperature probe on it, and it'll have a relay inside that you could attach to a heater of some sort, a silicone heater or a capsule heater, all that stuff that I told you about. This box is a PID controller, which is to say that it's a device that all it really does is try to read the current temperature and get the output to drive that heater as hard and as fast as it can without overshooting, without undershooting, all that stuff. A PID controller stands for proportional. Ooh, I don't like writing it like that. Sorry. PID, proportional integral and derivative controller. What it actually is 3 controllers in one that are all sensitive to different parts of the signal. To remind you guys what an integral and a derivative is, okay? An integral is essentially solving the question on how much space, how much surface area is underneath this curve. Okay, if I asked you how many square millimeters is hashed on this board, you could probably take a ruler to it and roughly figure it out. Okay, the way that that's done is by blocking this off into individual rectangles, just like this. Can you guys see that from there? You see that I'm kind of building it up in stacks of bars that, when pushed together, kind of make that curve. So imagine each of these has some width, call it 1 inch, and then this would have some length that changes for each bar, right? This first bar might be like 6 inches, this one would be 7 inches, and then you could do 1 times 6 plus 1 times 7 plus 1 times whatever, and you could figure out the area that way, right? An integral drives this 1 inch slice infinitely close to 0 inches, right? So each slice is like 1.000000001 inches thick by some height. Sum all of those slices together that are infinitely small, and you'll start to approximate an infinitely perfect approximation of the area underneath this curve. That's all an integral is it's taking infinitely small slices of a continuous signal to figure out how much area is underneath that curve. That's all it is. Okay? A derivative is kind of like this infinitesimally small slice of something. Okay, when we talk about a derivative of time, it's like when we're talking about 1 instant in time versus the very next instant in time. Okay, practically that's like 0.000 whatever to the 1 seconds later, but practically, mathematically, we call that the derivative, the next instant. Okay, another way to think about this is the slope, the change of a signal. Okay, the derivative at this point would be this slope, the derivative at this point would be this slope, derivative at this point would be this slope, and so on. That make sense? Okay, so those concepts known, I'm going to show you guys a video on what PID actually does and how it works. It should be the last video for today. Second to last, I lied.
Welcome back to Control System Lectures. In this video, we're going to begin our conversation on PID control. This video is just an introduction to the topic and will hopefully provide some good background information on PID controllers. Now, to describe what PID control is and why we use it, let me first describe more generally what a controller is. And one way to write an open-loop system is like this, where inputs act on a plant for the system to be controlled, and then some output signal is generated. Often in these open-loop scenarios, the performance of the system isn't good enough to meet your requirements. Let me give you an example of what I mean. You're tasked to build a robot that needs to move from this spot here over to this red X. You could figure out how fast the robot moves, and then from that determine how long the robot needs to drive for before it gets to the red X. This type of commanding is called open loop because the amount of time the robot drives is not adjusted based on the actual position of the robot. And open loop commanding is perfectly fine for systems that don't change much or where accuracy isn't as important. However, what if there's some dirt in one of the wheels and the robot veers off to the side? Or if the robot's slightly faster than you had predicted? In both of these cases, the robot won't stop on the red X because it has no way of compensating for these errors and making adjustments on its own. Now the solution then is feedback control, which essentially means you're sensing the output of the plant and feeding it back so that the system can make adjustments accordingly. Now in a feedback system, there's a reference signal, and this is the desired value or the ultimate goal. And you compare that to the measured value, and what you're left with is the error or the delta between where you are and where you want to be. So in the case of the robot, the error would be the difference from the reference position, which is the distance from the start to the red X in meters, and the robot current position, which is measured by the robot, also in meters. So at this point, we need to figure out how to convert an error signal that has units the same as the output of the plant into an input signal that has units that may or may not be the same as the output. And in addition to just changing the units, the error needs to be adjusted in such a way that the input into the robot causes it to eventually reach the red X. And this is exactly what a controller does. It takes the error signal and converts it into a command that is then sent into the plant. And one of the goals of a control engineer is to design this controller so that as time progresses, the error, or the difference between the current location and the goal, is driven to zero. And zero error means that the measured position is exactly where you want it to be, which means that the system meets all of its requirements. Well, at least this particular one. Now there's many types of controllers, and we're going to touch on a lot of them as these videos progress. However, in this lecture, I'm only going to talk about PID controllers and its variations. I'll explain what I mean by that in a second. The PID controller is a great place to start because it's simple, efficient, and effective in a wide array of applications. In fact, it's the majority of controller types in industrial applications, so it's well worth learning. Let me start with the term PID. PID is an acronym, and it stands for proportional, integral, derivative. And each of these terms describe how the error term is treated prior to being summed and sent into the plant. In one of its block diagram forms, a PID controller can be written like this. In the proportional path, the error term is multiplied by a constant Kp. In the integral path, the error is multiplied by Ki and then integrated. And in the derivative path, it's multiplied by Kd and then differentiated. The three paths are then summed together to produce the controller output. Now the three K terms are called gains, and they can be adjusted or tuned to a particular plant with a defined set of requirements. And by changing these values, you're adjusting how sensitive the system is to each of these different paths, either the P, I, or D path. Let me explain what I mean with a few plots here. Let's say the error in the system is changing over time, like this red line. In the proportional path, the output is the error scaled by the gain Kp. So you can see here that when the error is large, the proportional path will produce a large output. When the error is zero, the output in the path is zero, and when it's negative, the output is negative. In the integral path, as the error moves over time, the integral will continually sum it up and multiply it by the constant Ki. In this plot, it's easy to see that the integral path is the area under the curve, where this blue section is positive area and this green section here is negative area. Now the integral path is used to remove constant errors in a control system, since no matter how small the constant error, eventually the summation of that error will be significant enough to adjust the controller output. Now in the derivative path, it's the rate of change of the error that contributes to the output signal. When the change in error is moving relatively slowly, like it is at the beginning here, then the derivative path is small. And the faster the error changes, the larger the derivative path becomes. Now at this point, you can just sum up each of these three paths and you've got the output of a PID controller. But you don't always need all three paths. You can remove a path completely by setting its associated gain to 0. When you do this, you generally refer to the controller with the letters of the path that are left. For example, you can have a proportional integral controller, or PI, if you set KD to 0, and just a P controller if KD and KI are both 0. So why would you simplify the controller like that? Why not just make the biggest, best controller you can with all paths intact and super complicated? Well, typically when I'm designing a control law, I try to make the logic as simple as I can while still meeting all design requirements. I do this for several reasons. 1 is a simple controller is easy to implement. 2, a simple controller is easy to tune, test, and troubleshoot when there's problems. And 3, a simple controller is easy for other people to understand, which is important when you work in a large project and interface with other groups that have to buy into the control logic. For example, a software or hardware team that has to implement it. So simple controllers can save you time and money over the life of the program, as long as they still meet your design requirements.
All right, so a little bit more on this. For why exactly is PID desirable, especially in PLC land that we live in. It's really great because if we have a messy signal, for example, if we have just a temperature controller, right? If we have all kinds of stuff going on, ventilation going on, other heaters going on, whatever, that would be normally difficult to try to, we just have a heater to command that heater to adjust the heat to try to get as close as possible to our set point, right? It would take a lot of code, I think, and a lot of time to manually, with structured text, make a program that would cause our heater to respond to changes and to, as quickly as possible, get to that set point. But we don't need to do that. We don't need to spend those hours because some wonderful person has created a PID block that we can wire a sensor value into and wire a sensor output from, or a motor command output from, and all we need to specify it is 3 numbers, P, I, and D. Literally numbers, tags, so like P will be 0.1, I might be like 0.005, and D is usually 0. We usually only use PID, or I only use like the PI portion of it, and D is set to 0, but it can be set to whatever you want. And then the thing that determines how well and how fast and how little overshoot and all that stuff is boiled down to three numbers. And if you can figure out the correct 3 numbers to put here, your system will perform wonderfully. And if not, it'll perform terribly. Okay. The idea of figuring out what these numbers should be is called PID tuning. Okay. Oftentimes it's a manual process where it's you sit down and tweak these numbers and see how the system responds and tweak them again and see if you get a better response. There's also more advanced techniques that we've determined algorithms and things where the system can test itself and tweak itself until it optimizes itself. But the idea, again, in general, why is a PID controller so great is because it boils down this complicated control process problem into a block that with 3 dials on it, right? 3 tweakable settings that if you tweak them correctly, it'll more or less work. Okay. One more thing before we go on. I'm going to show you one more video guide by this guy. He's going to show you a PID example, but I wanted to make sure we really understand each of the parameters, P, I, and D. Okay, so you guys should understand that what's actually happening is we have our input, and it's kind of like it's being fed into 3 different brains. We have the P brain, we have the I brain, and then we have the D brain. Okay, think about our speed control system. Okay, if we have a PID speed controller, we have a certain mile per hour coming in, and we want to respond. We want to respond with how hard we should drive the motor. right? Call that motor force. Okay, and what's going to happen is that each of these brains, P, I, and D, are going to see the same input and respond differently. They all have their own personalities. How are they going to deal with where we are versus where we want to be on our set point? The way that P responds, the way that he was telling you in this video, is that it's very reactive. Okay, if it sees that we're slowing down, it will try to speed up the motor. If we slow down by half, it'll increase by half. If our P is set to 1, okay, that's how we scale it. All right, if, for example, we need to push back twice as hard as we are being pushed, we would set P to 2, and then it would respond twice as hard to any disturbances. That's all the proportional controller does. Okay, so if we go this way a little bit, it responds in kind. The downside of the proportional controller, the proportional brain controlling things, is that it can't correct over the long term. Imagine our tilt situation again. For example, we have a tilting device right here. We can figure out what this angle is, theta, but we want it to be perfectly upright. We want it to be at 90-degree angle. If we use a proportional controller to do this, okay, gravity or some force was pushing it this way, but our proportional controller was correcting it back this way, it very well could come extremely close, okay, where if we zoom in on this, okay, that like where we are and where we want to be are very, very, very close, okay? But the P controller doesn't have any means to reduce this gap. It will always be this amount off, that amount shy, because it can't dynamically respond to this. It's sensing that we're here, and so it's moving accordingly, and the result of that, those two forces meeting, is that small amount of error. Okay, this is where our integral controller comes in. Okay, our integral controller, the integral brain, really doesn't like being off for long periods of time. It gets progressively more mad, okay? So in this situation where we're a little bit off, okay, in our speed controller situation, it would be like if we're traveling at, if we want to be at 45 miles an hour, but we're at 44, we're just a little bit off, okay? The way that integral controllers work is that it continually adds up this little error, okay? So it'll add this error to this error to this error at every instant in time, okay? So the sum of that will start to grow over time as we keep compounding these errors, okay? So if our error sign, which I'm going to draw in red, you know, it starts here because we just added here, and then we add it more, and then we add it more, and we add it more, and more, and more, and more, and more, and more. And after, you know, some amount of time t, we now have a large command signal, that's this line, that says, hey, I'm commanding firmly for the motor to make up this difference, for you to push a little bit harder. This line would drift up, the error would go back to 0 or drift down towards 0, and then the I term would calm down again. It says, okay, I'm happy where we are, you don't need to change. So in our tilt example, where we were before, if we got really close with our P controller, over time, as our integral term adds up, rises and rises and rises, we would see our tilt kind of slowly shift back towards the center. It would slowly error correct. Excellent thing to have in a process control, right? Something that over time will kind of drift towards where you want it to be. That's what the I term does. It's really useful, okay? The D term is not often used. Like I said, most things can be accomplished with the P and I only. So P would, you know, again be set to anything between 0 and 100. Really, it doesn't have an upper bound. It's just how hard you want it to respond to things. And if you set it to 0, it removes that controller. So if you didn't want that, you know, that creeping motion, that creeping error correction to be in there, you could set it to 0. If you wanted it to creep fast or slow, oh, I should go over this too. If your I is really high, if it's a little bit too aggressive, if it gets mad a little bit too fast, it'll oscillate. So what'll happen is we'll have this process control. We'll be here, right? We'll be coming along here, and the eye controller will go, oh, we're a little bit off. I'm getting mad. And then it goes, oh, we're a little bit over. All right, we should go down. Oh, I'm a little bit under. We should go up. And then it keeps kind of going like that. It keeps swinging, so oscillating. It's one thing that can happen with the I term. The D term, the derivative, is really good for dealing with disturbances. It's the rate of change. So if proportional counters how much is changing, the derivative counters the rate of how much it's changing, the change of the change. Okay, that's what we're talking about over here for the slope of the curves at that point. Okay, so this brain pays attention to the changes at each point in time. Okay, so the thing that the output of each of these controllers, for example, if our peripheral controller says we're here on our tilt table, but we should be here, it says you need to push this hard. Okay, that might be like 30% of our motor power. Okay, the integral controller would also add on top of that. It says, you know, we've had this amount of error for 5 seconds. I really want to correct that. I'm saying we should add 50% motor power. The D term might be set to 0, so it's like, I don't really care, 0% power. And then the power that comes out of this motor and actually gets commanded is summed together. That's what they're talking about for this sum term. So how hard is P saying we should push? How hard is I saying we should push? How hard is D? And then all that is summed out. So in this case, we would respond with 80% motor force to try to correct back to our position. Okay, any questions? Cool, all right, yeah.
Is it like a line of succession thing where you start with the P and the I, or is it all continuous?
They're in parallel. So it's like one instant in time, we have an input for that instant, and it gets fed into each of these and gets summed for that instant before moving on. Yeah. All right, so I'm going to show an example, one more video on this guy, and then we'll have a little bit of time for our lab, if you guys want it. Yeah.
Welcome back to Control System Lectures. In this video, I'm going to continue discussing PID controllers by walking you through a thought exercise that's commonly used to explain PID control. During this example, we'll try to use reason and logic rather than math to see how PID controllers and their variations are used to generate the desired system response. For this example, you're driving your car, which is the plant, and you use the gas pedal to control the velocity of the car. We'll call the angle of the gas pedal theta, where the angle of 0 is when your foot isn't pressing on the pedal. Now I want to create a real simple model of the car to work off of so that if you want to verify our results of this exercise on your own, you can. We need a transfer function from the gas pedal position to the velocity of the car. Now in real life, this is a complicated nonlinear transfer function that's dependent on the car model. However, you can simplify this model by assuming it's just a first-order low-pass filter. And the transfer function for a low-pass filter looks like this, where the output is velocity and the input is angle. So let me explain why this is a reasonable estimate. If you press the gas pedal down halfway, the car would start to accelerate and then eventually settle at some constant speed and stay there. And I can say that any position of the gas pedal, if you held it there long enough, would result in a constant velocity that corresponds to that pedal position. And if you pressed it down just a little bit more, then that speed would increase a little bit faster. But here's where the low-pass filter comes in. If you press the gas pedal down slowly, which is the red line, then the car will be able to change its velocity according to the pedal position, the yellow line. But imagine if while you were driving, you started pumping the gas pedal all the way down to the floor and back up. The car wouldn't have enough time to respond to that, and the velocity would stay relatively constant. Therefore, low-frequency inputs are passed to the output, whereas higher-frequency inputs produce an output that is much smaller. And this is the signature of a low-pass filter. But our model isn't complete at this point, because no one drives by knowingly putting the gas pedal at a specific angle. You don't think to yourself, I need to go 20 miles per hour, so I'll put the pedal at 10 degrees. Instead, people drive by applying a change in pedal angle. For example, you realize you're driving a little slow, so you change the angle of the gas pedal by pressing it down a little bit more. So our command is actually change an angle over time, which can then be integrated to produce an angle which is the input into our low-pass filter. So the transfer function from the change in the gas pedal angle to the velocity of the car is then combined and would look something like this. So keep this model in mind as we go through the exercises. In this first example, we're going to go over proportional control. The closed-loop control system for our car with a proportional controller would look something like this, where the error is the difference between our reference command and the measured signal. And the error is fed into our proportional controller. Now imagine that you're sitting in your car stopped at a stoplight, and the speed limit for the road that you're on is 25 miles per hour. The light turns green and you begin to press on the gas pedal to accelerate up to the speed limit. Now in real life, as you drive your car to respond to this step command, you're unknowingly performing proportional control. Here's what happens. Initially, you're commanding 0 miles per hour. And once the light turns green, your reference signal steps up to 25 miles per hour. At this point, you have an error of 25 miles per hour. And this is a large error, so you apply a large change in the gas pedal proportional to that error, and you press the pedal fairly fast because of that. Now, as your velocity increases towards 25 miles per hour, your error gradually gets smaller and smaller, so you gradually slow the rate at which you press the gas pedal. And eventually the car reaches 25 miles per hour, and since the error is 0, you stop adjusting the pedal and you hold it constant. Now at this point we can reason that with proportional controllers, the steady state error will be 0. So with that in mind, try to imagine what would happen if the gain was too large in this example. Now initially the vehicle is at rest, and then the light turns green and there's a step up to 25 miles per hour, same as before. And this is a large error, and instead of pressing on the gas pedal slightly, you floor it because of the high gain, and before you have time to register that you've pressed the gas pedal too far, your car is all the way up to 50 miles per hour. Now at this point, the error is now minus 25 miles per hour. So you slam on the brakes, and again, before you have time to realize your speed, the car is stopped, and then the cycle starts all over again. And by increasing the gain, you run the risk of making your control system unstable. Perhaps you or someone you know already drives like this, where they apply too much gas or too much brake all the time. If that's the case, then you can tell them that maybe their gain is a little bit too high. Okay, so let's look at another example now. This time let's add the derivative term to the control system, but we'll change the problem just slightly. It's the same start as before, where you're sitting at a red light, but now there's another stoplight just down the road that's also red. In this example, you're trying to control your position instead of speed, so that when your light turns green, your reference position, which is where you want to be, steps up from 0 to the position of the next light. In the block diagram, this would equate to adding an integrator right here at the end to convert from velocity to position. And so now this is the new transfer function for the system in this example. Also, your reference signal would change from speed to a position, since this is what you're trying to control. So now let's apply a proportional controller to that and see what happens. Again, your reference position would step up to the position of the second stoplight. And since initially your error is large, you apply a large proportional change in pedal angle. The car begins to accelerate, and as you get closer to the stoplight, the error gets smaller and smaller, and the magnitude of the change of pedal also gets smaller. Eventually you arrive at the light, and right when you're there, the error goes to 0 because you're at the position you want and you stop changing the angle of the pedal. So everything's okay, right? Wrong. Not only do you have all that acquired speed, but you're still pressing the pedal down and you blow right past the light. Now once you pass the light, the error begins to grow negatively, and you start releasing the pedal, and eventually you put the car in reverse and start heading back to the light. But you have the same problem in that direction, and you end up just oscillating back and forth. So the next time you run a red light, you can just tell the officer that you only ran it because you drive with a proportional controller, and that's just what it does. Of course, more than likely, the officer will just say, "Tell that to the judge," and is going to hand you the ticket anyway. But you can avoid all of that mess by using a proportional derivative controller. When you add the derivative term to the controller, making a PD controller, you're adjusting the change in angle of the pedal based on the rate of change of the error as well as the magnitude. In other words, you recognize that you're closing in awfully fast on the light, so you better start releasing the gas pedal a bit early. It works like this. At the beginning, you have lots of error, and you aren't moving, so the proportional path is large and the derivative path is 0. Once you start accelerating towards the second light, the error gets smaller, but is still positive, so you continue to press the pedal further, but more slowly than you did before. In addition, you're starting to close in quickly on the second light, so the time rate of change of the error is getting more negative. The result is that the derivative path causes you to slow the change in pedal angle. Eventually, the error is small enough that the proportional path contributes less than the derivative path, and you start to slow the car down, and this occurs earlier than your reference position. And if you've tuned yourself properly, which loosely means that you know how to drive, then you're going to stop right at that second light. Now, one way to think of the interaction between proportional and derivative is that the proportional path tries to get you to the destination as fast as possible, while the derivative part is trying to restrain you from moving too quickly. In this case, it takes the balance of the two to properly stop the light. Finally, let's put the entire package together and look at PID control. Let me quickly rewrite the closed-loop control system here so that we have a starting point for what I'm about to say. Now remember at the beginning I said no one drives by commanding an angle to the gas pedal. Rather, they drive by commanding a change in the angle. Well, in this example, we'll command an angle, and I'll show you why that's not a good idea. And then I'll show you how PID control can help in that situation. Let's say you're in your car and you're trying to drive right beside your friend who's moving at a constant speed. In this case, the reference signal is the position of your friend. If the output of the controller is a pedal angle, it's easy to see that there's going to be a steady state error, and you will always trail behind your friend and never beside him. Imagine this. You're some distance behind your friend and you're both going the same speed. In that case, you have an error signal that looks like this. And since the error isn't changing over time, remember that your speeds are matched, the derivative path is 0. And let's assume that the error in the proportional path causes you to press the gas pedal down to its current location. In this situation, you're not going to move the pedal at all, and you'll continue to drive behind your friend, since your velocities will still be matched. So now you might be thinking, maybe your proportional gain isn't high enough. If it was, you could go a little bit faster and catch up to your friend. If you increase the gain, then the proportional path will cause you to press the gas pedal down to a new lower position. And you'll drive a bit faster, catching your friend. However, as you get closer, the error gets smaller, and so you begin to release the pedal, causing the car to slow back down again. So by increasing the gain, all you've done is shorten the distance between you and your friend, which is the steady state error. But you haven't removed the error. You can easily see the flaw in this thinking by assuming you started out at the exact speed and location as your friend, and you use a PD controller. In this case, both the proportional and derivative error terms are 0, so you immediately release the pedal and start slowing down. So by controlling pedal position and using a proportional derivative controller, we have no way of bringing the steady state error to 0. Now this is where the integral path comes in handy to remove steady state errors. When you are trailing behind your friend and the error is constant, the integral path will slowly build up error, adding more and more pedal to the output. It works like this. The error starts out constant just like it was before. And just like before, you're holding the pedal exactly where it already is, and you're trailing your friend. But since the error term is non-zero, the integral path is summing up that error over time and gradually increasing the pedal's position. Eventually, as you close the gap with your friend, the proportional term will be 0, since there's no error, you're exactly equal with your friend. The derivative term will be non-zero since you're closing the gap with your friend, but if you're closing slow enough, it won't have much of an effect on the output. But the important thing is that the integral term is going to be held constant at the exact pedal position that you need. And this is how all three terms are used to control a large variety of control problems. And I use this car example to illustrate it because most people can relate to it, and you can actually imagine the system reacting to different controllers.
But keep in mind that these examples are analogous to many systems in real life. If you have a good understanding of the dynamics in the system, then it's possible to reason through the problem to determine what type of controller you need. However, choosing a controller is only part of the solution. You now have to tune the controller in order to meet your system requirements. And in these thought exercises, we really only looked at one of those requirements, and that is whether the error in the system eventually reached 0. However, in a real system, you tune the controller for much more than that. For example, you might be concerned with overshoot or rise time or settling time. And I'll cover how to tune PID controllers in future lectures, and we'll touch on each of those requirements and more. But for now, I hope this gave you a little bit more intuition on how each of these 3 paths in a PID controller contribute to the overall control system. And as always, thanks for watching.
All right. Any questions on that? Did that help make a little bit more sense? Cool. All right. So made really good time today. For those of you who need it, I'm going to give you the last half hour of today to work on your lab if you want it, to complete it. We don't have to work on it, at the lab time or at the makeup time. You have some time today to do so. For those of you who don't wish to do so, you're welcome to stick around, mess around with the controllers, ask me questions, but that's it for the lecture for today. All right. Thank you, guys. I'll be here. Let me know if you have any other questions. Otherwise, I'm at your disposal, okay?
We're working on the second half of the lab 1 from last week.
Yes, sir. Mm-hmm.
All right, cool. We were doing it during the lecture. What happened to that?
Sorry, what?
I was doing it during the first part of the lecture.
If you're completely done with the lab, then you're done for today. I can check it later. That's fine. Yeah, if you have any questions, let me know. You're Andrew, right? Okay. Just wanted to make sure I got you for attendance. Yeah.
No, I was here the whole time. I was just in the back.
Oh, gotcha. Okay. Gotcha. Okay, Ramon, you're not here. Angel, you're not here. Nope. Okay. Cool.
Yeah. I just waited 2 minutes. I could have just
You're working on the structured text lab on Wednesday?
Yes, that's correct. Or sorry, the structured text component of this lab. You could work on it today if you wanted to. I had something else in mind for this weekend, or for this Wednesday. But yeah, if you finish the first part, definitely go ahead for the structured text for sure.
I did the wire diagram. I finished that last week.
Mm-hmm.
So
I'll be right there.
I finished this one already just now. So
Then yeah, you're okay.
okay, all right.
Mm-hmm.
Have a good day.
You too. Question?
Yeah, so my problem last time was the run switch. So now I fixed it, I believe. So when E-stop or overpressure
Nice.
or temp is triggered, then once run switch is triggered, it's
So
stopping it from all happening.
you should always have at least one LED lit. So something's not quite right.
Oh, okay. So then what I did was just I added a run switch in there because I thought run switch needed to be at least. So,
Okay. That might be true, but I'm just saying we should always be in one of the 3 states: alert, caution, or run. So because no LEDs are on, we're not on any of those states.
Okay.
But really close. That's looking good. And then once you got that done and that's working, then go on to the structured text part of it. Yeah. You guys good to go? Any questions?
Still trying to figure out how I downloaded the file. I can't. How do I open it back up in here?
File.
I downloaded the zip file from the.
Oh, okay.
lab.
So then, so go to that zip file. Just go in your file browser. Yeah.
Ah,
That's not it. No, it'll be .zip. Yeah, so right click and then, oh, you didn't actually click it yet. And then, actually, no, click on this pink part and then extract.
Oh, you have to actually extract.
You have to actually extract it, yeah, and then you should be able to open it.
Okay.
I'll put the cheat sheet up on the projector for you guys for that example for structured text. Okay, so here's that structured text example. Hopefully that's helpful. We won't actually need a timer, a delay for this. It's just the if else and ands and ors and that kind of stuff. Don't be afraid to ask Google for cheat sheets as well.
structured text?
Sure, I could show you that. So you're gonna go new project, blah, blah, blah. Right click that guy, add new program, and then you want ST for structured text. And make sure to put it in the fast task group too. Right, fast task group.
How do I use the if statement? So I'm using if LEDY or LEDR, then I want LEDG to be off.
So you would do if first statement or space or second statement space then.
Yeah.
Yeah.
How do I? What would I put after to make LED off? The LEDG off.
So then that would be your else, right? So if that's where you want it to go on, you would go else light is off, light is false. And so here's an and example. I keep trying to click on it. Can you see it? I wonder I can. Oh, nice. There we go. Okay, so here's the and. This is the else if, but you can imagine this says if counter is greater than 5 and counter is less than 10, then do the thing. This would be like turn your output on, otherwise or else turn it off.
Okay. So then it would just be if LEDY or LEDR, then LEDG equals false.
To turn it off.
Yeah.
Right.
Question.
Yes, sir.
And or help.
Yeah.